the last video, we learned how to differentiate and integrate power series. We learned that you can do it term by term as long as you are strictly inside the radius of convergence. And a natural question to that is, so what? This video is all about the answer to so what. We'll learn what good this theorem is. So for example, suppose you get a problem that you are asked to compute the integral from 0 to 0.1 of 1 over 1 minus x to the fourth dx, and you're asked to do it to 6 decimal places without cheating and using Wolfram alpha. Now, you can do this integral. You can do it by partial fractions. It's 1 minus x squared times 1 plus x squared, and then you wind up with an arctangent, and you wind up with a log of 1 minus x, you wind up with a log of 1 plus x, and it is messy. I don't think that anybody would really want to do that by hand. But there's a really simple solution using power series. See, we know that 1 over 1 minus x to the fourth is just 1 plus x to the fourth plus x to the eighth plus x to the 12th plus x to the 16th and so on. Well, that means that the integral of 1 over 1 minus x to the fourth is x plus x to the fifth over 5 plus x to the ninth over 9 plus x to the 13th over 13. And if we want to evaluate that integral at 0.1 and at 0, well, at 0 gives you 0. And at 0.1, you get 0.1 plus 0.1 to the fifth over 5. And the next term is 0.1 to the ninth over 9. That is a 1 in the 10th decimal place. So not only are we going to, so if we ignore these things, not only are we going to be good to 6 decimal places, we're going to be good to 9 decimal places. All we need to do is to take the first two terms, and then all the other ones are really, really, really small. So we plug in the first two terms. 0.1 plus 0.1 to the fifth is 0.00001 divided by 5 is 0.00002. Add them together, and there you go. You got our answer. You got the integral to 6 decimal places, and it was easy. The next thing we're going to do is we're going to find power series for some common functions. So we already saw that 1 over 1 minus x is 1 plus x squared plus x cubed plus x to the fourth and so on. In other words, this is a sum from n goes from 0 to infinity of x to the n. Well, what if we wanted to understand the function 1 over 1 minus x squared? How are we going to get that? The key observation is that 1 over 1 minus x squared is the derivative of 1 over 1 minus x. So to get the series for 1 over 1 minus x squared, we just take this series and take its derivative term by term. Derivative of 1 is 0, derivative of x is 1, derivative of x squared is 2x, x cubed is 3x squared, x to the fourth is 4x cubed. And so, there we go. We've got the series for 1 over 1 minus x squared. By the way, in probability, expressions like this come up all the time. And you can reverse the process and say, oh, I see this power series and I recognize that it's the series for 1 over 1 minus x squared, and so I can evaluate it. Okay, let's take another one. We already saw that 1 over 1 plus x is given by this. So what about the integral of 1 over 1 plus x? The integral of 1 over 1 plus x dx is natural log of 1 plus x, plus a constant. And that's got to be x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4, and so on. And if you plug in x equals 0, you get c plus the log of 1. The log of 1 is 0, so c equals 0 minus 0 plus 0 plus, so c is 0. So we now have a formula for the natural log of 1 plus x. So if you want to know the natural log of any number between 0 and 2, see, this has a radius of convergence of 1, so this has a radius of convergence of 1. So x has to be between negative 1 and 1, so we're taking the log of something between 0 and 2. If you want to understand the log of any number between 0 and 2, just plug it into this power series. In fact, it even works on the boundary. The theorem said that everything worked on the interior, but you had to be careful on the boundary. In this case, it happens to work on the boundary. And the log of 2 is what you get when you plug in 1, which is 1 minus a half plus a third minus a fourth plus a fifth minus a sixth. We've seen this series several times. We saw it with alternating series, and we saw it several times thereafter. And I mentioned, by the way, this happens to be the natural log of 2. This is why it happens to be the natural log of 2. The next example is we look at 1 over 1 plus x squared. Well, that's 1 minus x squared plus x to the fourth minus x to the sixth plus x to the eighth minus x to the 10th. And if we integrate everything, the integral of 1 over 1 plus x squared dx is arctangent. And that gives you x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9th over 9th, and so on. And by the way, if you happen to plug in x equals 1, the arctangent of 1 is pi over 4. So here's a formula for pi. Pi is 4 times 1 minus the third plus the fifth minus the seventh plus the ninth. It's not a practical formula for pi because this converges really, really, really slowly. But it is a formula for pi. The moral of the story is that series give you really fast and accurate results. If you want to know, say, the natural log of 1.2, boom. All I need to do is write out the first 4 terms, and I'm going to get the natural log of 2 to 4 decimal place accuracy. And computing the first 4 terms is just basic arithmetic. 0.2 squared is 0.04, divided by 2, that's 0.02. 0.2 cubed is 0.008, divided by 3, you can do that. 0.2 to the fourth is 0.0016, divided by 4 is 0.0004. So, by just manipulating power series, you can get very, very accurate things. And in fact, this is how your pocket calculator actually works. If you ask it for the sine of an angle, or the log of something, or the exponential of something, the way it computes it is almost always involving some sort of power series.